Welcome back to Nick's Algebraics. Today, I'm going to talk about energy conservation. With me today, I have Random Guy.
Hello, I'm the random guy you all know and love.
Before I get into energy conservation, let me talk about potential energy. When you lift a heavy rock, for example, you're doing work, right? And that work is stored as energy in the system. And that energy can be released as kinetic energy if you let the rock fall. So, energy can be associated with the position of objects in a system, and this is called potential energy. So, it's the energy associated with position. So, potential energy is a measure of the potential or possibility for work to be done. So, if you raise a rock into the air, there's a potential for the gravitational force to do work on it if you allow the rock to fall.
That could potentially happen.
It's a possibility. So, we can define different types of potential energy, and each type is associated with a particular force. One example of potential energy is gravitational potential energy. The gravitational potential energy associated with a particle is defined as the product of the object's weight, so mg, and its height y above some reference level. Another example of potential energy is elastic potential energy. So, for an ideal spring, so that's a spring that obeys Hooke's law, the elastic potential energy stored in that ideal spring is defined as 1/2 kx squared. So remember, k is the spring constant and x is the displacement from equilibrium. Basically, how much did you stretch or compress it from its natural length? Let's answer this question here. How does the work done by the gravitational force on a particle of mass m relate to the change in the gravitational potential energy? So, the work done by the gravitational force, we know it's F times S times cosine phi. So, F, the force, is mg. It's the magnitude of the gravitational force. And S is the magnitude of displacement, and we have cosine phi. So let's say we have an object and it's falling from y1 to y2. The only force acting on the object is gravity, so we have mg, and the displacement is going to be in the same direction as the force. All right. So what does that make phi?
Can you explain again what phi represents? It's the angle between what?
Yes, that's a good point. So phi is the angle between the force, which is mg, and the displacement.
Well, that would just be 0 degrees.
Yeah, the angle between these two vectors is 0 degrees since it's parallel. So phi is 0 degrees. Now let's figure out what S is. The object's going from y1 to y2, so the displacement is just final position minus initial position. So it's y2 minus y1. But this is the magnitude of the displacement. So if I put y2 minus y1 like that, y2 is less than y1. So this would be negative. So since I'm dealing with the magnitude of the displacement, I'm going to put an absolute value on this.
Shouldn't you put absolute value in the original formula? Oh, it's the magnitude of force times the magnitude of displacement times cosine of the angle. That just follows from basic vector math, you know? It's
Yeah.
just the formula includes absolute values or like norms.
Well, S is the magnitude, though. It would be kind of redundant for me to put absolute value on the magnitude. Like in math, the way we do it, you know how we do it. We say this is the vector S and this is the magnitude of vector S. But like in physics, it's like, okay, this is vector S, and the magnitude of that vector is just I just write.
Yeah, I see what you're saying.
All right. Anyway, so I'm gonna put absolute value because it's magnitude and it has to be positive. Okay, so the absolute value of y2 minus y1, that's just y1 minus y2, right? Because y1 is greater than y2, so this would
Yeah,
be,
this will be positive.
yeah. And cosine of 0 degrees is 1. So now what I can do is distribute mg, and this looks very familiar. Mgy1, that's just the gravitational potential energy at y1. This is just ug1, and mgy2, that's just ug2. So this is the same thing as negative delta ug, because delta ug means UG2 minus UG1, but this is the other way around, so that's why there's a negative there. So that's how the work done by the gravitational force relates to the change in the gravitational potential energy. We have W sub g equals negative delta UG. All right, now let's do this question. How does work done by the elastic force relate to the change in elastic potential energy? Remember from the last video that the work done on a Hooke's law spring by an external force to stretch it from x1 to x2 is W equals 1 half k x2 squared minus 1 half k x1 squared. So this is the work done on a spring. And the work done by a spring is just going to be the opposite of this. You just have to switch these two terms. So W sub S is just going to be 1 half kx1 squared minus 1 half kx2 squared. So this is work done by a spring. And 1 half kx1 squared, very familiar. That looks like the elastic potential energy at x1. So I can write this as Ws equals us1 minus us2. And us1 minus us2, that's just negative delta u sub s.
You could just known that by looking at it. It's just the same as the formula above for gravity, except now it's a spring.
You know what? I am so sorry for doing this two-step derivation. I didn't mean to inconvenience you so much. I should have just skipped straight to this from that and said, "Oh, just replace G with S." I apologize. Sorry for doing a derivation for my students.
You could have left that as an exercise to the viewer, like all the textbooks.
Well, I'm different. I'm built different. Anyway, so that's how the work done by the elastic force relates to the elastic potential energy. All right. So now let's talk about conservative and non-conservative forces. A conservative force is a force for which the work done is independent of the path and depends only on the initial and final positions. So the gravitational force and the spring force are classic examples of conservative forces. There's another conservative force, which is the electric force between charged objects, but we're not going to talk about that today. So it doesn't matter whether an object falls straight down, like from y1 to y2, or if it slides down a ramp, because the work done by gravity is going to be the same since the starting and ending points are the same. It's just going to be mg times the initial position minus the final position. The same thing is true for ideal spring. So stretching the spring from x1 to x3 and then letting it go back to x2 does the same net work as just going directly from x1 to x2, because it's a conservative force and the only thing that matters is the initial and final positions. All right, so a conservative force allows the complete two-way conversion between kinetic and potential energy with no loss. So the work done is reversible, and the energy stored as potential can be fully recovered as kinetic. On the other hand, non-conservative forces, this is a force for which the work done depends on the path taken. So most forces are non-conservative. The classic examples are friction, tension force, or applied pushes or pulls. Let's say you have a block and it's sliding down a straight path, like down a ramp with friction. So friction is going to do negative work, right? Since the displacement and the frictional force are going to be anti-parallel. But if the same block slid along a like longer, curvier path with the same initial and final positions, then the work done would be even more negative since the path is longer. So it's not going to be the same, even though the endpoints are the same. So the work done by friction, that depends on the path. And with friction, the lost energy is converted into heat and it cannot be recovered. So non-conservative forces are irreversible. So that's what I wrote right here. Energy is dissipated as heat, sound, etc. One other thing is there's something called mechanical energy. So the total mechanical energy of a system is the sum of its kinetic energy K. So remember that's 1/2 mv squared and its potential energy U. So now the question is, when is the total mechanical energy of a system conserved? So to answer this, we have to start with the work energy theorem. So remember, the total work done equals the change in kinetic energy. And the total work done, that's the work done by the conservative forces plus the work done by the non-conservative forces. The only conservative forces that we're going to see in this video and that you see in a lot of introductory physics classes are the gravitational force and the spring force. So I'm going to break this up into W sub G and W sub S. So it's a mini assumption there that the only conservative forces that we're dealing with are gravity and the spring force. And we know that W sub G is just negative delta UG, and W sub S is negative delta US. And negative delta UG, that's just UG1 minus UG2. And negative delta US is just US1 minus US2. And I'm going to write the delta K as K2 minus K1.
I have a question.
Sure.
Is love a conservative force?
Oh, the force of love. I think it's pretty path dependent.
Good answer.
So what I can do now is let me get all the stuff with subscript 1 on one side and everything with subscript 2 on the other side. I'm going to add K1 to both sides, and I'm going to add UG2 and US2 to both sides. So you're going to get this. So this is our energy equation that we're going to use in this video. And remember, this is assuming that the only conservative forces acting on the system are the gravitational force and the spring force, which is a pretty safe assumption for introductory physics classes. Okay, so what does this look like right here? Kinetic energy plus the potential energies?
Mechanical energy.
Yeah, this is just the mechanical energy. This is the total mechanical energy of the system. So this is E1. So E1 plus the work done by the non-conservative forces is just E2 because this is kinetic energy plus the potential energies. So back to the original question, when is the total mechanical energy of the system conserved? So it's conserved when E1 equals E2. So the only way that would happen is if the work done by the non-conservative forces is 0. All right, so let me write that down. So the total mechanical energy is conserved. So that means E1 equals E2 when only conservative forces act on the system. So if there's only conservative forces, that means the work done by the non-conservative forces is 0. All right, very important concept. I think we're ready to do an example now.
A vertical spring of negligible mass with spring constant K equals 1,550 newtons per meter is fixed to the floor. A 1.10 kilogram ball is released from rest at a height of 1.05 meters above the top of the spring. What is the maximum distance the spring will be compressed?
Let's draw a picture of what's happening. So let's say this is the floor and we have a spring that's fixed to the floor. And there's a 1.1 kilogram ball released from rest at a height of 1.05 meters above the top of the spring. So this is the top of the spring right here. And we have a ball that's 1.05 meters above that. So I'm going to call that H equals 1.05 meters. And we're trying to figure out the maximum distance the spring will be compressed. So the ball is going to land on the spring and it's going to compress some maximum distance. So let me draw that separately here. All right, so it's compressed some maximum distance and we'll call that distance D. All right, so I'm going to call this 1. 1 represents when the ball is at rest, 1.05 meters above the top of the spring. And this will be 2 when the ball lands on the spring and the spring is at its maximum compression. So let me write my energy equation. So let's ask ourselves, what are the forces that are acting on the ball?
Gravity at first, and then the reaction from the spring.
Yeah, we have the spring force and we have gravity. So we don't have any non-conservative forces. There's no like friction or tension or anything like that. So WNC
Work, North Carolina.
is 0. And let me write out everything else. So K1, remember K is just 1 half mv squared. So this is 1 half mv1 squared. Gravitational potential energy at 1 right here. So remember from the first page, U sub G is just mgy. I will define y equals 0 as this right here. You can make anything y equals 0. If this is y equals 0, then initially the ball is d plus h above y equals 0. So mgy in this case is mg d plus h. US1, remember, that's the elastic potential energy. So that's 1 half kx squared. So plus 1 half kx1 squared. So what is x1? Remember, x is the displacement from equilibrium. So initially, the spring is at its natural length. It hasn't been stretched or compressed. So x1 is 0. All right, so this is going to cancel out. And then we have k2. So that's 1 half mv2 squared. And ug2, remember, ug2 is just mgy2. All right, so at 2, the ball is at the y equals 0 line. So that means y2 is 0. So this is going to cancel out. And lastly, US2, that's 1 half k x2 squared. X2, remember, we're trying to figure out the displacement from equilibrium. So this is at equilibrium at its natural length, and it just got compressed a distance d. So that means x2 is negative d because it just went down d. It got compressed. Basically, my positive direction is going to be upward. That's what I'm defining it as. We're trying to find D. Do we know anything about the velocities? Let's look at the problem. It says that the ball is released from rest. So that means V1 right here is 0. So we can actually cancel this out. And what's going to be the speed of the ball when the spring is at its maximum compression?
0.
Yeah, 0. So V2 is also 0. So I can cancel this out as well. I'm just canceling a bunch of stuff out.
Cancel culture. It's a real thing.
Yeah. So these are the only 2 things we have left. We have mg times d plus h equals 1 half kx2 squared. And remember, x2 I said is negative d. And if you square negative d, you just get d squared. So this is going to equal 1 half k d squared. All right, so let's solve for d. So to solve for d, I'm going to distribute the mg. So you get mgd plus mgh. And what I'm going to do is get everything to one side. All right, so we have k, we have the mass of the ball, we know g, we know h. So we can solve for d. This is just going to be a quadratic equation. So let's plug everything in and see what happens. So if you put this in your calculator, you're going to get 775 d squared minus 10.791 d minus 11.33055 equals 0.
That's a quadratic equation, all right.
Yep.
Only there were a formula for that.
Yes. So I'm definitely not factoring that. So we're going to use the quadratic formula to find d. If you use the quadratic formula, you're going to get two solutions, and one of them is going to be negative. So we're going to ignore that one because d is distance and it's greater than or equal to 0. So d is about 0.128 meters.